Hello friends, today we'll see periodic table chapter 1 periodic properties and variations of properties from 10th standard ICSC board chemistry. Let's see the introductory part of this periodic table chapter. Introduction: why we need periodic table. So need arose to group elements into families whose elements shows maximum resemblance. Second, on such an arrangement in the form of table, properties of element were seen to reappear at a regular interval in the table. So why we need periodic table? So the elements which are having same property, we can arrange them uh, linearly, or we can resemble them with the help of their chemical properties, and for that periodic table is required. Then classification of periodic table. So early chemists arrange elements on the basis of valency, metallic and non-metallic character. Method discarded as elements showed variable valency and dual character. So earlier attempts to design periodic table was based on valency and metallic and non-metallic character of that particular element. Then Dobrenier in 1815 arranged elements in increasing order of their atomic weight. Atomic weight is nothing but number of proton plus number of neutrons. So Dobrenier arranged elements in increasing order of atomic weight at 1815. At that time only 30 to 35 elements were known. Elements were arranged in groups of 3 called triads. So he made triads, that is a group of 3 elements based on their atomic weights. Atomic weight of the middle element was found generally to be the average of the other two. Means if we take average of the first and third element, if we take average of atomic weight of first and third element, we'll get atomic weight of second element. So that was Dobrenier triads. Method was discarded since it did not hold true for all elements. So only 3 to 4 triads were made. Around 9 to 12 elements are there in triads, and other elements are not following the triad, and therefore this Dobrenier triad theory is failed. Then next attempt was by Newland in 1864. He arranged element in increasing order of atomic weight. So principal method is same. Dobrenier also arranged elements in increasing order of atomic weights, and Newland did the same thing. Elements were arranged in a series of 8. So in case of Dobrenier, triads were there, 3 elements, and here elements are arranged in the series of 8. Properties of every 8th element was found to be a repetition of the first element. So it is like octaves, musical octaves, sa re ga ma pa dha ni, and again sa comes. Okay, or in case of Western, do re mi fa sol la ti do. So properties of every 8th element was found to be similar to that of the first element. Method was discarded as it failed to leave spaces of for undiscovered element. So there are too much limitation in Newland's theory, and one of the limitation they have given now, that spaces for undiscovered element were not there. Other limitations were also there, and that's why this theory is failed. At the time of Newland, 56 elements were known, and Newland thought that no new elements will be discovered after that, and that's why no empty spaces kept in Newland's periodic table. After Newland's periodic table, next up is Mendeleev periodic table in 1869, and Mendeleev arranged elements in increasing order of atomic weights. So that is number of proton plus number of neutrons. So if you see the principle of all the three, Dobrenier, Newland and Mendeleev, all depend upon increasing order of atomic weights. Let's see the next point of Mendeleev. Elements were arranged in the form of table, and that table is called Mendeleev's periodic table. Okay, so the periodic table of Mendeleev is known as Mendeleev's periodic table, and he stated that properties of elements were periodic function of their atomic weights. So depending upon atomic weights, properties of elements differ. Those properties are chemical as well as physical properties. At that time, chemical properties are related with the reaction with hydrogen and oxygen. So hydrides and oxide are of each element were studied, and accordingly they put in the Mendeleev periodic table. Method could not justify position of certain elements, rare earths and isotopes. So again there are limitations for Mendeleev's periodic table. Isotopes were not written in that periodic table. Certain elements position is very ambiguous, and rare earths where to write rare earth elements. So Mendeleev could not explain that. And after Mendeleev's periodic table in 1912, Henry Moseley is the scientist who discovered modern periodic table, and that modern periodic table only which we are following now. So Moseley in 1912 arranged elements in increasing order of atomic numbers. So see the first three, Dobrenier, Newland, Mendeleev, they depend upon atomic mass number, their periodic table. But Henry Moseley's periodic table depend upon atomic number. Henry Moseley's periodic table is also known as modern periodic table, and it depends upon atomic number, that is number of protons or number of electrons. Elements were arranged in a modified table called modern periodic table. So elements were arranged in a periodic table known as modern periodic table. He stated that properties of element were periodic function of their atomic numbers. Method removes most of the defects of Mendeleev's periodic table. So see, this is the modern periodic table. There are total 18 groups in the modern periodic table and 7 periods. The sixth and seventh period are very much extended, so the remaining elements are written below. So this modern periodic table divides into 4 blocks, namely S block, P block, D block and F block elements. Group 1 and group 2 of the modern periodic table comes under S block. Group 3 to group 12 comes under D block. Group 13 to 18 comes under P block, and lanthanide and actinide series, that is from 6th and 7th period, the part of 6th and 7th period, lanthanide and actinide series, collectively known as F block. So it is divided into 4 blocks, and here you must remember that modern periodic table in modern periodic table 18 groups are there and 7 periods are there in modern periodic table. And for 10th standard point of view, you must remember periodic table at least till calcium. So first 20 elements you should know till calcium from 10 by 10th point of view. And if you take science after that, then you have to do the whole periodic table. Now let's see the introductory part of modern periodic table. Introduction. Mendeleev had arranged elements in periodic table on the basis of increasing atomic weights that we saw previously. Mosley modified Mendeleev's periodic table and stated that the basis of classification of element be according to the increasing atomic numbers and not atomic weights. So he studied physical and chemical properties of each element, and he stated that elements should be arranged in at increasing atomic number and not in atomic weight, number of electrons and their arrangement. So that number of electron is nothing but atomic number only. Atomic number is equal to number of electrons or number of protons. Atomic number is equal to the number of electrons in the energy shell of atom. Hence atomic number is a fundamental property of element. Modern periodic law. So this is the statement: physical and chemical properties of element are periodic function of their atomic number. So this is the modern periodic law statement. It could come in exam. So the statement is physical and chemical properties of elements are periodic function of their atomic number. So if modern periodic law is asked, then you have to write down this. Then let's see the salient features of modern periodic table. First, we already know periodic table based on the uh, basic fundamental property, that is atomic number. Then position correlates position of an element with its electronic configuration. So by electronic configuration we can easily arrange this periodic table. So it depends upon electronic configuration. Position methodological arrangement or methodical arrangement arranges element in increasing order of atomic number. So atomic number increases and elements are arranged according to that. 7 horizontal rows are there in modern periodic table and they are named as periods. 18 vertical columns are also there and they are named as groups. The 7 horizontal rows called periods and 18 vertical columns are called groups. Then periods. Completion of each period is logical since each period begins with the element having one electron in the outermost shell and ends with the zero group element having completely filled outer shell. So this zero group element is nothing but noble gases. So it ends with noble gases helium, neon, argon, krypton, xenon, radon, and start with the one which is having electronic configuration in the last shell 1, that is hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Completion of each period is logical since each period begins with the element having one electron in outermost shell and ends with zero element having completely filled outermost shell. A transition from metallic to non-metallic character is thus seen across the period. So across the period, non-metallic character increases and metallic character decreases. Then in case of groups, each vertical column, known as group, accommodates element with the same outer electronic configuration, hence having similar property. 18 vertical columns consist of groups 1 to 17 and 18 is the zero group. Group 1, 2 and 13 to 17 are called normal elements that come under S and P block. So S and P block are collectively known as normal elements. 3 to 12 are called transition element. Group 18 is at extreme right, contains noble or inert gases, so it is known as zero group element. Sometimes it is taken in P block, in some textbook it is not taken in P block, and in some textbook it is taken in P block. Okay, so it is a zero group element, group number 18. And they told that the electronic configuration is same. So for that we can take example of lithium, sodium, potassium. So atomic number of lithium is 3, electronic configuration is 2, 1. Atomic number of sodium is 11, electronic configuration 2, 8, 1. Atomic number of potassium is 19, so 2, 8, 8, 1. So if you observe the outermost shell, the electronic configuration is same, that is 1, and similar to that all the elements were arranged in the periodic table. So elements with the same electronic configuration are in same group. Separation of elements. So how to separate these elements? Reactive metals were there. You studied reactive metals in your ninth standard. Reactive metals are placed in group 1 and group 2. Transition elements, metals, are placed in the middle, and non-metals are placed in the upper right corner of the periodic table. So position is explained. Then next is periodicity of elements. Gradual change in the properties is seen with increasing atomic number in the periodic table. So as atomic number increases, property will get changed. Periodicity in properties, that is recurrence in properties, are seen with elements belonging to the same subgroup in the periodic table after a difference of 2, 8, 18 or 32 in atomic numbers due to recurrence of similar valence shell electronic configuration. So these are the three reasons for periodicity in properties. Now periods are described. So periods are the 7 horizontal rows of element arranged in increasing order of their atomic numbers. Period number 1, 2, 3 signifies no electron shell of an element. Period 1 contains hydrogen and helium. Period 2 starts with lithium and ends with neon. Period 3 starts with sodium and ends with argon. So they have written shells also. In hydrogen, atomic number is only 1, so 1 electron is there, and shell is also 1. Lithium, atomic number 3, so 2 shells are involved. First shell contains 2 electron and second shell contains 1 electron. Sodium, atomic number 11, so 11 electrons were there, and it consists of 3 shells. First shell contains 2 electrons, second shell contains 8 electrons, and third shell contains 1 electron. So that you have learned in your ninth standard again. The 7 periods of the modern periodic table. So they are written 7 periods. Type of period: first 3 are short, 4, 5, 6 and 7 are long. Number of elements: outermost element are 2, 8, 8, 18, 18, 32, and last one 26 is given because further elements were discovered later only, so they were not printed in this textbook. Otherwise it will be also 32. Then atomic number 1 and 2, then 3 to 10, 11 to 18, 19 to 36, 37 to 54. See the difference of 18. Then 55 to 86 and 87 to 112. It should be till 118 now because the remaining elements were discovered and the elements were written. You must know the first 20 elements at least for your 10th standard. Bridge elements in period 2. Bridge elements show similarity in properties diagonally with the period of the next group. So that relationship is known as diagonal relationship. Here bridge element is lithium and magnesium. So they are diagonal but they show similar chemical properties. So such elements are known as diagonal elements or bridge elements. Beryllium, aluminium is there, boron, silicon is there. Next again we'll see period in more detail. Property trends of elements from left to right in a period. Similarity: number of electron shells. So electron shells remain fixed in a period. So if we consider lithium and beryllium, so lithium is having atomic number 3 and beryllium is having atomic number 4. So lithium's electronic configuration is 2, 1, means last electron is present in the second shell. And if you see beryllium, atomic number 4, electronic configuration 2 comma 2. So last electron enters on in the second shell only. So the last electron is having same shell, and therefore we can say the shell is similar. Okay, for period 1 it is K shell, for period 2 it is L shell, and so on. I have given example of lithium sodium, I have given example of lithium, beryllium and all. Then transition, valence electrons non-metallic character increases by 1, non-metallic character increases. So valency increases by 1 across the period. So let's take example of that second period only. Lithium is having atomic number 3, so electronic configuration 2 comma 1, so valency is also 1. Beryllium atomic number 4, electronic configuration 2 comma 2, valency is 2, outermost shell. So valency is increased now, from 1 it becomes 2. In case of boron atomic number 5, electronic configuration 2 comma 3, so valency of boron is 3. Then carbon 2 comma 4, so valency is 4. So till carbon valency is increased. And if we see after carbon, nitrogen is there, atomic number 7, 2 comma 5. So valency is 3 now, because 5 electrons are there in outermost shell, and giving 5 electron is difficult than taking 3 electron to become stable, and therefore nitrogen shows valency 3 in most of the cases. So valency first increases by 1 and then starts decreasing. Period 1 hydrogen and helium. Period 2, so elements are given, electronic configuration of those elements were given, state is also given. So see, the metallic character decreases and non-metallic character increases. And now see the valency, first it increases till 4 and then it decreases. Period 3 is similar to period 2, all the properties. Electronic configuration increases by 1, atomic number increases by 1, state changes from metallic to non-metallic, valency first increases till 4 and then decreases. Okay, so they show same valency: lithium, sodium, beryllium, magnesium, boron, aluminum, carbon, silicon, then nitrogen, phosphorus, oxygen, sulfur. So they were in same group and therefore show similar valency. Fluorine, chlorine is there, neon, argon is there. And then their compounds were written depending upon that electronic configuration and valency only. We can write down structure of this compound. You already learned that in your 9th standard. NaCl, MgCl2, AlCl3, SiCl4, PCl3, PCl5, S2Cl2. So if you observe carefully, covalent character increases from left to right and ionic character decreases. Ionic character or ionic bond is electrostatic force of attraction between oppositely charged ions, and covalent bond or covalent character occurs by sharing of electrons. So sharing of electron property increases from left to right and ionic character decreases. Then states are given, their oxides were also given. Oxides are also written depending upon their valency and oxidation state. Bonding, electrovalent, first 3. Electrovalent means ionic only, and the next are covalent character increases, therefore bonding is covalent. Then basicity decreases from left to right, acidity increases. After that, hydroxide formation. So that also depends upon valency on oxidation state. NaOH, then magnesium is 2 plus OH is minus 1. So formula will become MgOH twice, and so on. Hydrides, NaH, MgH2, AlH3, SiH4. So they are also similar. That's it. Some more examples were written below. So that's all for period. And then next is groups in the modern periodic table. So total 18 groups were there in modern periodic table. We already discussed that. Group number signifies the number of valence electrons of an element. Group 1, then group 2 is there, group 3, so that depends upon valency of that element. Group 1 contains valency of all elements as 1, group 2 valency of all elements is 2, and so on. The groups of modern periodic table. So group 1 is known as alkali metals. Group 1 is also known as alkali metals. There are total 18 groups. First group is known as alkali metals. Meaning of alkali metals is they form basic oxides. The metals which form basic oxides are known as alkali metals. Example is given, lithium to francium. So you can clearly see this first group, lithium to francium, all are alkali metals. They form basic oxides. And when bases dissolve in water, they are known as alkali. So the name of element is alkali metals. Alkaline earth metals. Alkaline earth metals are the group 2 elements. So why group 2 elements are known as alkaline earth metals? Alkaline because they also form basic oxides, and earth metal because they are predominantly found in earth crust, therefore they are known as earth metals. So in combination we can write alkaline earth metals. They form basic oxide, also they are found in earth crust, and therefore they are known as alkaline earth metals. From beryllium to radium, beryllium, magnesium, calcium, strontium, barium, and radium. Then 3 to 12 are known as transition elements, that is from scandium to zirconium. Next up is inner transition elements. Inner transition elements are from lanthanum to uh, lutetium, and actinium to lawrencium. So that inner transition elements are known as lanthanide and actinide series. Group 6 and group 7 are known as inner transition element, and they are also known as F block element. And transition element generally consist group D, D block elements, and they belong to group 3 to 12. 13 to 16 are P block element, and they are also known as post transition element, from aluminum to antimony, Al to Sb, sorry, aluminum to titanium, germanium to lead, and antimony to bismuth. So we saw in the form of groups. So aluminum to titanium, germanium to lead, that is Pb, antimony to bismuth. Next is halogen, fluorine, chlorine, bromine, iodine, astatine. Group number 17 is always known as halogens, and group number 18 is known as noble gases or inert gases. Then transition element, same thing is given there, lie between electropositive metals on the left and least electropositive elements on the right. So they are at the middle between metals and non-metals. They all have similar properties. Inner transition elements, they told from cerium to thorium, that is from lanthanide series. Two horizontal rows of metals at the bottom of the table, and those two series are known as lanthanides and actinides. So you should know the names. Okay, what are transition elements, what are lanthanide series, what are actinide series, where they are placed. Period 6 and 7 belongs to lanthanide and actinide series respectively. D block are 3 to 12. P are from 13 to, generally we say that 13 to 18 is the P block, and so on. Noble gases, they are inert, they present in group number 18, that is last group, unreactive and has stable electronic configuration. So why they are known as noble gas? They do not react with anything. They are also known as inert gases: helium, neon, argon, krypton, xenon, and radon. Now next groups again continued in modern periodic table. So you can see the electronic configuration is same from lithium, sodium, potassium, rubidium, cesium, francium. So we will directly read the similarity. Valence electron of element in the subgroup remains same, and chemical properties also remain same because valence is same, so electronic configuration is same, and therefore chemical properties are also same. Then transition metallic character increases, and from top to bottom, and number of electron shell increase by 1 because the new electron enters into the new shell, and therefore number of shells get increased. For example, we can take lithium and sodium. Lithium is having electronic configuration 2 comma 1, so 2 shells are there in total. Sodium 11 number atomic number 11, so 2 comma 8 comma 1, so shells are 3. If we go to potassium, atomic number 19, 2 comma 8 comma 8 comma 4, so total 4 shells are there. Rubidium 5 shells are there, cesium 6 shells, francium 7 shells, so shells increase by 1. Then they told about alkali metals. So lithium, sodium, potassium, rubidium, cesium, francium are known as alkali metals. That is group 1, and also they told about halogen of group 17. You can remember alkali metals by phrase Lina ki ruby se friendship. So Lina is for lithium and sodium, Ki for potassium, that is K, ruby say friendship, that is for rubidium, cesium and francium. So that's how you can learn this group 1 alkali metals, Lina ki ruby say friendship, lithium, sodium, potassium, rubidium, cesium, francium. For group number 17, you can directly learn fluorine, chlorine, bromine, iodine, astatine. Valence is in both the cases, both have valency of 1 because of their electronic configuration. Nature, highly reactive, electropositive, light, soft metals. Metals are soft and hence can be cut by knife. You learned that sodium, we can cut the sodium with the help of knife. Why? Because those metals are soft. Alkali metals are generally soft in nature. Halogens are highly reactive, highly electronegative. Electronegativity is the tendency to attract electron towards itself. That is known as electronegativity. Then they are non-metals. All halogens are non-metals. Fluorine and chlorine are in gaseous state. Bromine is in liquid state. Iodine is in solid state at room temperature. Conductivity, alkali metals are good conductor of heat and electricity in solution state. Halogens are bad conductor or non-conductor of heat and electricity. Reducing or oxidizing nature. So reducing agents are the one which reduces the other element. Okay, they do not get itself reduced, they reduce the other element and they itself get oxidized. Strong reducing agent and strong oxidizing agents. Alkali metals, electron donors, have one valence electron which is easily removed from the outer shell, and therefore they are known as strong reducing agent. Halogens on the other hand are strong oxidizing agents. Electronegativity, low electronegativity, because these are electropositive elements. Electronegativity increases from left to right of the periodic table. And in case of halogens, electronegativity is high and electronegativity decreases from top to bottom. And we can say electropositivity increases or electronegativity decreases from top to bottom for both. In case of alkali metal, electropositivity increases and electronegativity decreases from lithium to cesium, and same for halogens. Electropositivity increases and electronegativity decreases from fluorine to iodine. Then reaction with non-metals, electrovalent compounds formed, example sodium chloride and potassium bromide. Covalent compounds form hydrochloric acid, phosphorus trichloride, S2Cl2 in case of halogens. When alkali metals react with hydrogen, ionic hydrides are obtained, and when halogen react with hydrogen, covalent hydrides are obtained. Then periodicity in properties is given. The modern periodic table, which is the arrangement of element in increasing order of atomic number based on modern periodic law, we already discussed that part. Properties of element are periodic function of their atomic numbers. We learned that. Periodicity in properties of element means occurrence of characteristic properties of element at definite intervals in the modern periodic table when elements are arranged in increasing order of atomic numbers. We learned that previously. Periodic properties. The properties which appear at regular intervals in the periodic table are called periodic properties, and the phenomenon is known as periodicity in properties of elements. That is the heading of the chapter. Periodic properties are atomic number, ionization potential, electron affinity, electronegativity, non-metallic and metallic character, density, melting and boiling point, nature of oxide, oxyacids and hydrides. So these properties are very important and highlighted part of this chapter. Most of the question came from these periodic trends only, and from the starting six trends, most of the questions come. That is atomic number, ionization potential, electron affinity, electronegativity, non-metallic and metallic character. Reasons for periodicity in properties, in periods and groups. So after definite interval of atomic number, similar valence shell electronic configuration occurs. Properties of element depend on the number and arrangement of electrons in various shell, including valence shell. In the same period or subgroup, increase or decrease in the period particular property is due to gradual change in the electronic configuration in the arranged element. And this is the table. So first is the atomic radius, periodic property is atomic radius, and meaning of the term. So what is atomic radius? It is the distance between the center of the nucleus and the outermost shell of an atom. So if you consider it as a circle, so from center of the circle to peripheral region, so distance between center of the nucleus and the outermost shell is known as atomic radius. Next is ionization potential. Next trend. What is ionization potential? It is the amount of energy required to remove an electron from the outermost shell. So how much energy is used, or how much energy is required to remove outermost electron from the outermost shell is known as ionization potential or ionization energy. It is the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. So example is given. If only one electron is there in the outermost shell, then the energy required to remove that is given there. M gives M plus plus E electron. Electron affinity is the amount of energy released when an atom in a gaseous state accepts an electron to form an ion. So it is opposite of that ionization potential. Electron affinity is the one is the amount of energy released when atom in the gaseous state accepts an electron in the form of an ion. Next is electronegativity. It is the tendency of atom to attract electron towards itself. I already discussed that. HCl example is given. So electronegativity is tendency to attract electron towards itself. In case of hydrochloric acid HCl, chlorine is more electronegative than hydrogen. So it accepts one electron of hydrogen by forming covalent bond. Then non-metallic character, you all know what is non-metal and what are metals. In terms of electron loss or gain, non-metal if it gains one or more electron, and metal if it loses one or more electron. Now first trend is explained here, periodic trends in property. The first trend is atomic size. So let's see the first trend, atomic size. We already discussed the definition of what is atomic radius, and unit of atomic radii is generally Armstrong. A naught is known as Armstrong unit. Atomic radius determines bond length. You can see that in figure. Factors which affect atomic size. So number of shells. As number of shell increases, atomic size increases. And reason for that is number of shell increases, the distance of outermost shell from the nucleus increases. So if we consider example of lithium and sodium, lithium is having only two shell, atomic number 3, electronic configuration 2 comma 1, so only two shells are involved. And if we consider the example of sodium, atomic number 11, so 2 comma 8 comma 1, so outermost electron is in the third shell, so shell is increased and therefore atomic radius is also increased. Then nuclear charge on an atom is the positive charge on the nucleus of an atom. It is equivalent to the atomic number of the element. In general, we can say that nuclear charge is the attraction of nucleus with the outermost electron. The attraction between the nucleus and the outermost electron is known as nuclear charge. And if we see the nuclear charge across the period, so across the period nuclear charge increases and atomic size decreases. So why nuclear charge is increased across the period? Number of shells are same. That is, if we take example of lithium and beryllium, so lithium is 2 comma 1, beryllium is 2 comma 2, so both are in same shell, that is second shell. But in case of beryllium, in outermost shell 2 electrons are there, and therefore attraction with nucleus is more. As the number of electrons were increased in the outermost shell, attraction with the nucleus increases, and therefore nuclear charge is also more in case of beryllium. And because of that more amount of attraction, the outermost shell or outermost orbital shrinks. Shrinks means it gets reduced in size, and therefore we can say across the period atomic size decreases. So trends in size, their atomic radii were given, radius were given. No need to memorize those atomic radius. Number of shell remains same, nuclear charge increases, atomic size unaffected, atomic size decreases. If we can say number of shell remains same, then atomic size is unaffected. If we say nuclear charge increases, then atomic size decreases. That is across the period. In period 2, lithium is the largest. Lithium has the largest atomic radius, and fluorine has the smallest. Neon has a larger atomic radius since it is inert gas. The outer shell is completely filled, resulting in force of repulsion. The effect of nuclear pull over the valence shell electron is not seen. Atomic size, that is radii, decreases across the period from left to right. Trends in atomic size down the group. So the down the group atomic radius increases, and atomic radius increases with the number of shell. With the increase in number of shell, atomic radius increases down the group. So that is written there. New shells added with increasing atomic number, nuclear distance from valence electron increases. Nuclear charge increases, atomic radius should decrease. But here what happens, the atomic shell part is more prominent than that of nuclear charge, and therefore that factor predominates. Atomic number of shells factor predominates the nuclear charge factor, and therefore atomic size increases. atomic size radii increases down the group. So in general we can say from left to right atomic size decreases due to increase in nuclear charge, and from top to bottom atomic size increases due to increase in number of shells. That is the conclusive part of this factor. Next factor is ionization potential or ionization energy. We already saw definition of that. The amount of energy required to remove a loosely bounded electron from the outermost shell of an isolated gaseous atom is known as ionization potential or ionization energy. We saw this reaction previously, and unit of ionization potential is electron volt, that is EV. Factors on which ionization potential depends. So atomic size increases, ionization potential decreases. Atomic size increases, the nuclear attraction of the outermost electron decreases, hence the outermost electron are loosely held and ionization potential decreases. So ionization potential is the minimum energy required to remove outermost electron. So if nuclear charge are increased, if the nuclear charge is increased, then the attraction of nucleus with the outermost electron is more. So we cannot remove that electron easily. Therefore, we can say that ionization potential decreases with increase in nuclear charge. So we can say from left to right, ionization potential decreases, and from top to bottom ionization potential increases. So nuclear charge increases, ionization potential increases. Reason nuclear charge increases, the nuclear attraction of the outermost electron increases, hence the outermost electron are more firmly held, that is ionization potential increases. So trends in ionization potential, you can see lithium, beryllium, boron. So ionization potential increases from left to right across the period. So atomic size decreases from left to right and ionization potential increases from left to right. Atomic size increases from top to bottom, ionization potential decreases from top to bottom. Atomic radii decreases, ionization potential increases. Nuclear charge increases, ionization potential increases. The element helium has the highest ionization potential while cesium has the lowest. Francium is the radioactive. Metal lose electron and generally have low ionization potential compared to non-metals. Ionization potential increases across the period from left to right, that we saw. And for down the group, atomic radii increases, ionization potential decreases. Nuclear charge increases, ionization potential should increase. But again, compared to the atomic radii factor, nuclear charge factor is less, or we can say atomic radii factor is more predominant. Because of that, atomic radii increases, ionization potential decreases down the group. Increase in atomic radii dominates over increasing nuclear charge. Overall ionization potential decreases. So ionization potential decreases down the group. So we can say the conclusion that ionization potential or ionization energy decreases from left to right. Sorry, ionization potential or ionization energy increases from left to right and decreases down the group. So the remaining part of this chapter will cover in next lecture. Thank you for watching the video.